All right, chapter 4 is our last mostly review chapter where we're going to discuss things that you should have already been exposed to in the MDT 101 class, maybe in other drafting classes you've had. If you've had the detailing class, even though this isn't a prerequisite for that, you have been exposed to these topics as well. What we're looking at with chapter 4 is the application of dimensions. The tail end of chapter 4, we're going to start talking a little bit about geometric dimensioning and tolerancing before chapter 5, which is where we go fully into GD&T. But chapter 4 is going to look at the application of dimensions in an engineering drawing. Now, this is an excellent chapter. This could be a whole class in learning how to apply dimensions properly. So it does have a lot of excellent material, and especially if it's going to be a review for you, just make sure that you understand everything and that you refresh your memory properly. I will also say, I think I mentioned it in the last lecture, that the proper application of geometric dimensioning and tolerancing requires the proper application of dimensions. Okay, so it is very critical. It's not review for the sake of review. It's review to establish a foundation that's necessary to build upon for geometric dimensioning and tolerancing. All right, that being said, so let's back up a second and understand what the job of an engineering drawing is. So an engineering drawing has two main objectives: to communicate the shape of a part and to communicate the size of a part. Okay, the shape description is handled with the orthographic views, right? And the orthographic views include standard views, top, front, right, left, bottom, back, those views, any section views, and auxiliary views. So that will describe the shape of the part. What we're missing in that, and what we need to completely communicate the design of the part so that it can be manufactured, is we need the size description. So the size description includes the location of the features, the size of the features, and any geometric form that are required. That is controlled through dimensions. Okay? So again, an engineering drawing is meant to communicate the shape and size of a part so that it can be manufactured. That is the definition of an engineering drawing, or the objective of an engineering drawing. Shape description is done with orthographic views. Size description is done with dimensions. We can go and continuing with dimensions, right? We can categorize the parts. We can categorize the features of a part as either features of size or non-size features. Okay, and this is a critical point to understand, because a lot of the GD&T tools that we're going to apply to a drawing, to a part, are based on whether that part is a feature of size or a non-size feature. Okay, a feature of size is basically a feature that we can touch. Okay, that is to say, it has diameter or depth or thickness. Okay, so a feature of size has diameter, like a cylinder. A hole would also be a feature of size because it has a diameter as well. A non-size feature is something that would be, for example, just a surface. Okay, so the surface of a part, a surface, would be a non-size feature. Now you might say, wait a second, that surface has a size, right? It has a length and a width, right? But we're talking about three-dimensional size. And a surface, technically speaking, has it is infinitely thin. There is no thickness with a surface. whereas a feature of size is a three-dimensional feature, a three-dimensional element of a part. So, and we talked about this in the last chapter. We can break the part, any part, down into its geometric primitive shapes, right? And these are features of size: cylinders, prisms, cones, spheres, wedges, toruses, which are donut shapes, and pyramids. And when we dimension, we should remember to follow two basic steps. Dimension the sizes of these individual geometric shapes, or features of size, and dimension the location of those features of size with respect to functional requirements and mating relationships. Okay? So, so when we look at a part, an imaginary part, right? And we looked at this part before in the last presentation. We can break it down geometrically. So this part here is composed of a rectangular box, a smaller rectangular box, a cylinder, four negative cylinders, right? These four holes are negative cylinders. Another negative cylinder right here. A negative cylinder that runs horizontal. A negative cylinder through the positive cylinder here, and then finally a negative cone. So that's going to help us to kind of step through the dimensioning process to make kind of an accounting list so that we can make sure that we have all the features dimensioned and we've dimensioned them properly. Further breaking these down and looking at these a little bit more in particular, even though they are basic shapes, and when we say they're basic three-dimensional primitives, keep in mind that a three-dimensional primitive will have three dimensions, right? A length, width, and a thickness. So here we see different ideas for dimensioning two views of a rectangular solid, right? A box, right? So in view A, we have a front view and a top view, and we can dimension the length and the height in the front view and the thickness in the top view. And here is just a reverse of that, where we're moving the dimensions to the left-hand side. Here's a front and a right side view. So again, two views. We only need two views to completely describe a three-dimensional shape. A basic three-dimensional shape, I should add. Here we have a length and a height, and then the thickness in the right view. And so you see, these are four examples of dimensioning a rectangular prism or a box. A cylinder, now if you remember back where I just said a few seconds ago that three-dimensional geometric primitives have three dimensions, and here you see, well, the cylinder has only two dimensions, a diameter and a height. Well, keep in mind that a diameter is two dimensions wrapped into one. Okay, so that's how that rule is applied properly here. But for this cylinder, we have the diameter and the height in the front view. Again, we're just reversing it. Here we have a front view and a right side view. Notice that, properly speaking, the diameter for a cylinder, a positive cylinder, should be dimensioned in its rectangular view, and that's what's being shown here. And so on and so forth. Okay, so we have wedges and cones and pyramids. This is a truncated pyramid. So those are some examples of how we dimension three-dimensional 3D primitives, geometric primitives. Now, talking a little bit more about some features, common features that we see. What about holes? So how do we dimension holes? Where we dimension holes with a diameter, right? And so here's four examples for how we can dimension a diameter. We can even place the diameter dimension inside the hole if it's a large hole. Outside the hole would be more common. If we have a couple of dimensions, we can orient them like this. Here we can use, in this case, we have a section view, and we're dimensioning the hole in the section view. This is not, strictly the optimal placement, but a lot of times you have to place the dimensions where there's room and space. Okay. So looking at some special holes, we have a counter bore hole. So here, a counter bore hole is a hole with, if we go back, this is an example of a counter bore hole where we have a larger diameter hole opening it up and then a smaller diameter hole going through. Okay. So back to this, here's the full dimension note for this counter bore hole. So we have a diameter of 0.25, which is the smaller diameter here. And it says through, even though that's strictly not required anymore. Then we have the counter bore symbol, diameter 0.5 for the diameter of the counter bore, the depth of the counter bore, there's the depth symbol, 0.25. And then the radius, 0.06, is just the radius on the, let me put it here again. It would be the radius in this corner right here. So the radius right there and right there would be 0.06. Okay. In the new standard, starting in the ASME Y145-2009 standard, the spot face symbol, which used to be the same as the counterbore symbol, they added SF, the letters SF inside the counterbore symbol. And that signifies a spot face. There is still no depth that we use with a spot face dimension. Countersunk holes, counter drill holes. So here we see a countersink dimension, or dimension symbol, I should say. A couple more rules with holes. So for the depth of a hole, assume the hole goes through unless the depth is specified. So we don't have to use the through symbol. It says when not clear, you can use the through symbol, but generally speaking, if there's no depth, then it's assumed to go through the part. Use the depth symbol for blind holes. A blind hole is a hole that does not go through the whole part. So in this case, we're using a depth symbol because this is a blind hole. Depth is specified always after the diameter. So here after the diameter, here after the diameter. The depth is the distance the full diameter extends into the part. So the depth here, 16, is from this surface right here to this line right here. Not to the tip of the cone, but to this line. Same thing here. This depth 3, is from the top surface here to this surface right here, the bottom of the counterbore. And finally, 118 degrees is the drill point standard. That's this angle right there. That can commonly be drawn at 120 degrees also. So it's not something that you measure or you worry too much about. All right, dimensioning radiuses, and what the difference is between a standard radius and what the tolerance is. So look at this example. We don't often look at tolerances. This class, that's all we're really going to look at is tolerances. So in this example, standard radius dimension, we have a radius of 0.07 plus or minus 20 thou, I should say, plus or minus 20 thou. So this radius can range acceptably between a radius of 0.05 and a radius of 0.09. And so here we see that application. So the red lines indicate the boundaries of that surface. Anything outside of the red lines is unacceptable. Now, there is such a thing as a controlled radius, right? And so a controlled radius is the same as a regular radius, except there's no reversals allowed. And we can vary it within the limits. Okay. What a reversal is like this example right here. So you see that kind of curve, see how it reverses, right? So we have the curvature that comes like this, and then all of a sudden the curvature reverses and goes the other way. Well, with a regular radius dimension, that is acceptable. With a controlled radius dimension, that is not acceptable. You can only have a non-reversal radius that exists between the two inner and outer limits of size. Chamfers, we all know what a chamfer is. A chamfer is just basically a turning down of a cylinder, whether it could be in a hole, it could be a positive cylinder like that. These are some examples of how we dimension chamfers. Okay, all of these are acceptable. All these are according to the standard. How do we dimension key seats and keyways? Well, here we go. These are some examples here. This is, by the way, I should say, this is a chapter that when you're dimensioning, you might want to flip to because it has good examples, right? And so it's not necessary that you memorize these, but you just know where they are in the chapter. So when you're dimensioning, you can double check your work or you can use it to apply dimensions properly. Symmetrical features. Symmetrical features can be indicated by having a line of symmetry or a center line that breaks halfway between two surfaces. In this case, you can see it the left and right, and we have a center line in between that. There's a symmetry symbol, which is, I don't think it's shown on any of this, but it's two horizontal lines going through the center line, okay? We want to dimension across the line of symmetry. So this 40 and the 50 and the 62, because they go across the line of symmetry, that means that the distance from the center to half of this, or to this outer edge, is 20, because it's the line of symmetry. That's the center line. Same with the 50. It would be 25 from here to here. Now, a critical thing is we do not locate the line of symmetry. What that means is this, and you've seen I've crossed it here, crossed it out. The 30.7 is not necessary. And in fact, the 30.7 will mess up, will completely invalidate the intended use of the line of symmetry. Okay, so we want to be careful. This is correctly dimensioned on the right-hand side. We are not missing any dimensions here. You do not need a 20 or a 25 or a 31 here. Okay? And in fact, that would be wrong. Here, the 30.7 is wrong. All right? The 61.4 is all we need. All right, now moving on to tolerance dimensions. There are, count them, 1, 2, 3, 4, 5 different types of tolerances that we can use in an engineering drawing. Limit dimensions show the upper limit of size and the lower limit of size stacked on top of each other or alternately in a line. Okay, that's acceptable as well. Equal bilateral dimensions are what we might call a plus-minus dimension. All right, so in this case, 57.20 plus or minus 0.80. By the way, how do we know that this is a metric dimension? Well, we have a leading zero here. Why do we have a trailing zero with a metric dimension when that is supposed to be against the rules? Well, because we want to carry 2 decimal places here. Okay. Unequal bilateral dimensions. Okay, they're plus-minus dimensions, but the plus and the minus are not equal. So in this case, the upper limit of size is 1.878, 6 plus 2, and the lower limit of size is 1.875, 876 minus 0.001. And then finally, we have unilateral dimensions. A unilateral dimension is an unequal bilateral dimension where one of the sides, either the plus or the minus, is 0. So the upper limit of size here would be 1.878. The lower limit of size would be 1.876. And I said finally before, but there is finally the last type of tolerance dimension, and that is a dimension, a single limit dimensions where you use the term, the phrase min or max after your dimension. So you would have the number, so for example, 1.878 min. Right? That means it can't go any less than 1.878, but it can go more than 1.878. Okay. This is important, there is no functional difference between these types of dimensions. So from a manufacturing point of view, they mean exactly the same thing. Exactly the same thing. The only thing that the tolerance dimensions provide us is the upper limit of size and the lower limit of size. Everything else is just gravy. All right. Now, why do we have these differences and why do we need them? Well, there are some ways that we can help the manufacturing process by using maybe a unilateral dimension where the basic size 1.878 is equal to the nominal size for the hole or the drill bit, and then the one-sided dimension here, the minus 0.002, indicates how much tool wear we'll accept on the drilling operation. So there's some little things like that where you can kind of help out in the manufacturing process, but functionally speaking, these are all equivalent in terms of conveying information. All right, so we talked about this in the last chapter 3. This is a review of that, which is a review from earlier classes. Decimal inch tolerances have no leading zeros, and we want uniform dimensional placement. That is to say, if we have 3 decimal places in the tolerance here, we want 3 decimal places in the basic size. Metric dimensions, typically in millimeters, we want to show leading zeros, and we want to truncate trailing zeros. So we don't put 120.000 and leading zero here 0.002. So we include that 0. These are examples, of course, of equal bilateral dimensions. This is a 3 decimal place tolerance, and we have 3 decimal places here. Notice we have 3 decimal places here and no decimal places in the 10. Notice also that the 20 has a 0 here. Well, wait a second. Truncate trailing zeros. Why do we have a 0 there? To balance out the 45. We have a 5. We have a decimal place there, the 5, and so we need a 0 there. That, of course, is an example of an unequal bilateral tolerance. Here we have unilateral tolerances. Again, 4 decimal places, 4 decimal places. Everything is easy peasy with decimal inch. With metric, okay, now we got some rule breakers here. So first of all, with metric, this is a unilateral dimension. We don't show any decimal places. Okay, weird, no decimal places. We also don't show the sign. Yeah, double weird, right? That is according to the standard. That's the rule. And finally, we have limit dimensions. So again, I mean, there's nothing really to talk about here. This is 4 decimal places, so those have to be 4 decimal places. And again, we balance it. So 3 decimal places here. The 8 means that we need to include a 0 to balance it out with a 3. Okay. Again, keep this chapter open when you're dimensioning. Keep this presentation open when you're applying dimensions, just to help you so that you can make this a habit and you can understand what you're doing each time. All right, now so that is the kind of the last of our dimensioning review. So let's go now and start talking about geometric dimensioning and tolerancing, and we're going to look at the first 2 rules. Okay. So rule number 1 with geometric dimensioning and tolerancing. This is ASME Y 14.5, rule number 1. A dimensioned feature must have perfect form at its maximum material condition. Okay? This means that a hole is a perfect cylinder when it is at its smallest permissible diameter, which is its MMC condition. A shaft is a perfect cylinder when it's at its largest diameter, which is its MMC size. Planes are perfectly parallel when at their maximum thickness. All right. So to paraphrase rule number 1 says you have to have perfect form at MMC. All right. So the other way to talk about this is called the perfect form boundary, or the envelope of perfect form. All right. So let's look and see what that means and how it's applied. So look up at the top, and we have an example of a dimension of a shaft. Okay. So here the shaft small little pin has a diameter of 10.8 to 10.6, right? So if we manufacture, remember that this is stating what the acceptable limits of manufacture are for this pin. So we can manufacture that pin at 10.8 millimeters in diameter, 10.7 millimeters in diameter, 10.65 millimeters, 10.6 millimeters, 10.61 millimeters. We can manufacture that pin at any diameter within that range. All right. But if we manufacture the pin at 10.8, it must have perfect form. What does that mean? Well, that means the shaft or pin in this case cannot bend. And the way to imagine that is going back to this, a perfect form boundary. All right. And this really helps me to understand the concept for this rule. So what would be the envelope of perfect form for a shaft? Well, it would be a hole. Okay. So imagine the shaft. If we make a perfect form to fit that shaft, it would be a hole. And that hole, in this example, in this case, would exist at a diameter of 10.8. Okay, so now we have a hole with a diameter of 10.8. We call that the boundary of perfect form. Why is it at 10.8? Well, that's the MMC size of the shaft. So if we have a hole with a diameter of 10.8, how badly can this pin be bent to fit through that hole? Well, if we make the pin at 10.8 millimeters in diameter, and we are trying to fit it through a 10.8 millimeter diameter hole, it can't be bent at all. That pin or shaft has to be perfect in its shape. It has to have perfect form. It cannot bend like this one does. As the pin deviates from its MMC size, that is, as it gets, in this case, smaller, as it gets to 10.7 and then 10.6, it could possibly bend and still get through that hole. Right? So if we make the pin at 10.6, it can bend the most, right? It could be out of perfect form through this bending and still fit through the hole. Now, if we switch up to rule number 1 applied to an internal feature, i.e. a hole. So in this case, we have a hole that's a diameter of 14.6 and 14.0 millimeters in diameter. So again, this is a range of acceptable sizes. We can make the hole any diameter within this range. But if we make the hole at its at its maximum material condition size, which is 14, remember for a hole, the MMC size is its smallest diameter. So if we make the hole at 14, it has to be a perfectly straight hole. It has to have perfect form. Now, how can we imagine that? Well, we can use the envelope of perfect form concept again. So the envelope for a hole, the envelope of perfect form for a hole would be a shaft or a pin, right? The opposite shape. And that shaft or pin would be at its MMC size, which is 14. So if we have a shaft or pin at the MMC size of diameter 14, and we try to get it through that hole, if we have the hole at 14 and the pin at 14, the hole has to be perfect to go through. Any deviation from diameter 14 for the hole, so as the 14 gets larger, as the hole gets larger to maybe 14.6, that hole can be way curved, be way bent. And we can still get the perfect form boundary, the envelope of perfect form visualized by the shaft at diameter 14 through that hole. All right, so that's what rule number 1 says. Here's another way to look at rule number 1. And these are the deviations, amount of form error allowed. So here we're actually calculating the amount of form error. All right. So we have this shape right here, right? It's a C channel. Doesn't matter what shape it is. It's still a feature of size. And it can range in height or thickness from 10.2 to 10.8. Because this is a positive feature, that is to say it's not a hole, we can touch it, the envelope of perfect form would be a slot that would be at its MMC size, or 10.8. Right? So the rule number 1 boundary, the envelope of perfect form, would be 10.8. So if we make this part and we make it at 10.8, the amount of form error is 0. It has to be perfectly flat and perfectly straight. If we make it at 10.7, it's allowed to bend slightly. How much can it bend? Well, 0.1, right? 10.7 plus 0.1 is 10.8. If we make the part at 10.6, well, now it can bend 0.2. So it can bend more, like this. 10.5, well, now it can have a perfect form error of 0.3. 10.4, well, okay, 10.3, now we're getting to a half a millimeter. And then finally at 10.2, what we would call the least material condition, the smallest size, acceptable size for this, we can have a maximum allowable form error of 0.6 millimeters. So it can bend 0.6 millimeters. Basically, that gap right there would be 0.6 millimeters. Now, there are some exceptions to rule number 1. And these are basically parts that cannot be expected to have perfect form. Typically, these are floppy parts, extremely long parts, and stock material. Okay? When size tolerance exceeds the form tolerance, that is to say, when we want to break rule number 1, when we want to say, yeah, we're not going to use rule number 1 here, we need to use what's called an independency symbol, an I, a circle I, and we put that adjacent to the size dimension. All right, we'll see some examples of that. And then finally, the last thing in this chapter, we talk about rule number 2, right? So rule number 1 is perfect form at MMC. Rule number 2 says that if no material condition is specified, then it is then the material condition is regardless of feature size. Okay, there's a typo right there. I'll fix that typo. Okay, basically, to summarize rule number 2, RFS, regardless of feature size and regardless of material boundary, is assumed unless you see an MMC or LMC symbol otherwise. Okay, so regardless of feature size is assumed for all tolerances. MMC, MMB, LMC, and LMB symbols must be shown in the feature control frame if they are intended to be used, applied. Right? And whoops, let me go back one. And the past practice of using an S, this circle S should be down here. For RFS is not allowed. All right, so that's a past practice. All right, well, I'm going to fix this presentation and re-upload it to Canvas, but that finishes our look at chapter 4. All right, so please read this chapter. Remember that this is intended as mostly a review, but it would be really good when you're doing your application problems and maybe some of the other problems to keep this chapter in mind, because it does have a wealth of information, just lots of good examples for you in the proper application of dimensions. All right, I'll see you in the next chapter.